Hello everyone, welcome to my YouTube channel. Today we will learn about operational amplifiers power supply rejection ratio. In this video, I am going to explain what is power supply rejection ratio, what is input and output offset voltage, how to measure power supply rejection ratio and common mode rejection ratio combined effect, some useful formulas in calculating power supply rejection ratio versus power supply ripple frequency, and finally operational amplifier power supply and decoupling methods. First we will discuss what is power supply rejection ratio. Let's take an operational amplifier. Suppose we have applied a power supply of plus or minus 15 volts to its respective power terminals. Now we have applied a differential input signal at its inverting and non-inverting terminals. As we know, Vin is equal to V1 minus V2. So the operational amplifier amplifies the differential signals according to its differential gain, and our output Vout is equal to differential gain into Vin. If this DC power supply have a ripple or noise of plus or minus 5 volt in its peak output voltage, so op-amp's power supply will get distorted. In practical condition, due to the noise in power supply, our output also gets distorted. Power supply rejection ratio or supply voltage rejection ratio is the term widely used in operational amplifier to describe its capability to reject or suppress any power supply ripples or variations in their output. Before discussing more about power supply rejection ratio, first we must know some basic concepts of offset voltage of operational amplifier. In my next video, I will explain offset voltage in details. If both input terminals of op-amp are connected to ground or we have applied 0 volts on input, then in ideal condition we must get 0 volts in its output. But in practical condition, we will get some measurable voltage like millivolt or microvolt at its output. This voltage is called output offset voltage of this op-amp. This voltage is a result of the imbalance in the operational amplifier. There are several methods that may be used to eliminate output offset voltage. One of these is to apply a voltage between input terminals so as to make output voltage 0. The voltage which we have applied at its input to make output voltage 0 is called input offset voltage. As we know, Vout is equal to gain into Vin. So the value of input offset voltage required to eliminate the output offset voltage is output offset voltage divided by gain. By using this formula, we can calculate input and output offset voltages of an operational amplifier. Let's observe how this offset voltage is used in measuring power supply rejection ratio. We have configured an operational amplifier as a unity gain amplifier and applied a plus or minus 15 volt to its respective power terminals. And to make output voltage 0, we have applied an input offset voltage of 250 microvolt between operational amplifier's input terminals. So the input offset voltage is 250 microvolt in this case. Now let's reduce the power supply by plus or minus 5 volt. So now operational amplifier have plus or minus 14.5 volt at its power terminals. In this case, to make Vout 0, our required input offset voltage is also gets reduced. Assume that input offset voltage is here 245 microvolt only. So the change in input offset voltage delta VOS is equal to input offset voltage VOS1 minus input offset voltage VOS2. 250 microvolt minus 245 microvolt, that is equal to 5 microvolt. Now the change in total supply voltage is delta V supply is equal to supply voltage Vs1 minus supply voltage Vs2. Vs1 is equal to total supply in the first case, that is 30 volt, minus Vs2 is equal to total supply in second case, that is 29 volt. The difference is 1 volts. The power supply rejection ratio is defined as the ratio of change in input offset voltage divided by change in supply voltage. Here change in input offset voltage is 5 microvolt divided by change in power supply is equal to 1 volt. That gives power supply rejection ratio value as 5 microvolt per volt. This means in this operational amplifier, if 1 volt change in total supply voltage will make 5 microvolt change in input offset voltage. Very often power supply rejection ratio is expressed in dB. Power supply rejection ratio in dB is equal to minus 20 log 10 into change in offset voltage divided by change in supply voltage. So here minus 20 log 10 into 5 microvolt change in input offset voltage divided by 1 volt change in supply. That comes 106 dB of power supply rejection ratio in this case. The data sheets of operational amplifier provides power supply rejection ratio or supply voltage rejection ratio values in dB. Here the data sheet of general purpose operational amplifier LM741 is showing supply voltage rejection ratio and input offset voltage values. Let us observe the combined effect of power supply rejection ratio and common mode rejection ratio when the operational amplifier's positive and negative supplies changes symmetrically and asymmetrically. First, look at the default test conditions shown here. This circuit has symmetrical plus or minus 15 volt supplies such that the average of two supplies is 0 volt. This is the default case, and shifts in offset voltage will occur if the power supply rejection ratio or common mode rejection ratio voltage shift from this configuration. In the second case, the supply voltage has been changed to plus or minus 14.5 volts symmetrically, such that average voltage is still 0 volts. In both first and second conditions, the common mode voltage with respect to ground is 0. So, this circuit also doesn't have common mode voltage because the supply change is kept symmetrical. The shift in offset voltage is 5 microvolt because of power supply rejection ratio. In the third case, negative supply is shifted to 14 volt, but positive supply is maintained at 15 volts. The average supply voltage is now 0.5 volts and the common mode voltage with respect to ground is still 0 volts. This constitutes a change of 0.5 volts in the common mode voltage, which introduces a common mode error as well as a power supply rejection error. So the input offset voltage change is 1 microvolt compared to the default test condition. The key thing to understand is that an asymmetric change in the supply voltage translates to a shift in the common mode voltage. A shift in common mode voltage will introduce a common mode rejection error. Here I have summarized mathematical formulas to calculate power supply rejection ratio and their definitions. To represent power supply rejection ratio in volts per volts, we use formula as change in offset voltage divided by change in supply voltage. To translate power supply rejection ratio into microvolts per volt, we must multiply power supply rejection ratio into 10 to the power of 6. By using law of logarithms, power supply rejection ratio can be expressed as a negative or positive values in dB, depending on whether power supply rejection ratio is defined as change in offset voltage divided by change in supply voltage or vice versa. There is no accepted standard for this. Both conventions are in use. For amplifiers with both positive and negative supplies are in use, the power supply rejection ratio for each supply voltage may be separately specified as power supply rejection ratio positive and power supply rejection ratio negative. But normally the power supply rejection ratio is tested with opposite polarity supply applied at both the supply terminals of operational amplifier. Otherwise, common mode rejection ratio will affect the measurement of the power supply rejection ratio. It is extremely important to remember that power supply rejection ratio is very much depends on supply voltage ripple or noise frequency. Like common mode rejection ratio, power supply rejection ratio is also frequency dependent and reduces with increase in power supply ripple frequency, and the slope is approximately minus 20 dB per decade. The typical values for power supply rejection ratio are in the 100 dB range for an op-amp. If operational amplifier is powered by a 60 Hz source, the output ripple frequency from a standard full wave rectifier will be 120 Hz. This ripple will be reduced by power supply rejection ratio of operational amplifier. Because operational amplifiers power supply rejection ratio is a frequency dependent, operational amplifiers power supplies must be well decoupled. At lower frequencies, operational amplifiers both power terminals must be decoupled with electrolytic capacitors of 10 microfarad to 50 microfarad, provided it is not more than 10 cm circuit track distance. For higher frequency operations, operational amplifier both power supply terminals must be decoupled by ceramic capacitors of 0.01 microfarad to 0.1 microfarad with short leads or circuit tracks. These capacitors must also provide return path for high frequency currents in the op-amp's load. That's all about power supply rejection ratio. So if you have any doubts or suggestions, please mention them in the comment section below. Thanks for watching this video. If you like this video, please click the like button, share this video, please subscribe and turn on notifications for more such videos. Follow me on my next video, offset voltage of operational amplifier. Have a nice day.